Hi, Mr. Brandt. This is the chapters 1 to 9 calculator retake for Calc BC. And another disclaimer, if I mess up, I apologize. I'm just going to roll through it. So the number one asks, use the Euler's method to make a table of values for the approximate solution of the following differential equation with the specified initial value. Use 5 step sizes of 0.05. Now, I use the Euler's method to find an approximate solution of the following differential equation by using the equation y of n is equal to y of n minus 1 plus h times f with x minus 1 and y minus 1, which is basically the same as saying y1 is equal to y0, which in this case is y is equal to 2, given by our initial value, plus the step size 0.05 times the y prime, which is 3 times 0, as we see here, plus 3 times 2. Now we repeat the process, and doing this gets us 2.3. Now we repeat the process for a y2, and then 2.3 becomes our new y n minus 1, because that's y1, plus 0.05 times 3 times the new x, which is 0.05, plus 2 times 0.3, because that's the y1 that we got back here. Doing this process over and over again, we get our answer to come as 4.106 or about 4.11, which makes C our answer. Number 2 asks, find the arc length of the graph of the function y is equal to x cubed over 6 plus 1 over 2x over the interval 1 to 2. To find the arc length of the graph of the function y is equal to x cubed over 6 plus 1 over 2x, over the interval from 1 to 2, I use the arc length formula, which is this right here. The integral from a to b of the square root of 1 plus y prime squared dx. I started by taking the derivative of y, which came out to be x squared over 2 minus 1 over 2x squared. And plugging that into the formula that we just read, as well as the interval values, the interval values from 1 to 2 of the square root of 1 plus x squared minus 1 over 2x squared dx. I then FOILed out the derivative of y squared to make it easier to plug into the calculator, which got me to here. The integral from 1 to 2 of the square root of 1 plus x squared over 2 minus 1 over 4 minus 1 over 4 plus 1 over 4x to the 4th power, which is the same thing as saying the integral from 1 to 2, the square root of 1 over 2, because that's this subtracted by this, plus x squared over 2 plus 1 over 4x squared dx. Then I then plugged that into the calculator, and that got me 1.575, which equals about 17 over 12, which makes C our correct answer. Also, sorry about the misplacings of the problems. I have to jump around a bit. I don't know why I did that, but it's just how it is. Number 3 asks, determine whether the improper integral from 4 to infinity of 2 over x cubed dx diverges or converges. Evaluate the integral if it converges. Since the function is in the p-series format and 3 is greater than 1, we immediately know that the function converges. So, diverges E is not an option. Since the integral is from 4 to infinity, we must take the limit as a variable approaches infinity, in this case b, because plugging in infinity doesn't necessarily work. After taking the integral, we get to, as you can see, we did the limit from b is equal to infinity, from 4 to b, 2 over x cubed, and then just put it in a more simpler form, and then we get the limit as b approaches infinity of 2 times negative 1 over 2x squared from 4 to b. Since 1 over infinity, or in this case b, is essentially 0, we cross it out. We then also distributed the negatives here, which made the first value negative and the second value positive, which is why this is a positive 1 over 4 squared. We end up getting 1 over 4 squared, which becomes 1 over 16, making B our correct answer. Number 4, find all values for x which a series from n equals 0 to infinity of 9 times x minus 8 over 9 to the power of n converges. Since this series is a geometric series, r, which is x minus 8 over 9, as we see right here, so this right here is our r, this value must be less than 1 and greater than -1 in order for the entire series to converge. Knowing this, I multiplied 9 on each side to get x minus 8 is less than 9 and x minus 8 is greater than -9. Adding the 8 on each side for both equations, I get x is less than 17 and x is greater than -1, which means that the interval for the values of x for the function to converge is the answer A, which is -1 is less than x is less than 17. Number 5. True or false? The series of n equals 1 to infinity of 6n over 4n squared plus 1 diverges. Basically what we see, I had to cross this part out, so what we see right here is what we're trying to find, whether it converges or diverges. Sorry about that. So to find whether or not this series diverges, I used a limit comparison test. I compared the series to b of n, which is 6n over 4n squared, because that's basically the same thing as this without the plus 1. The series then simplifies out to 3 over 2n, which diverges since p is equal to 1, and this is in the p series format. The p is right here, and the n to the power of 1, and means diverges. I then took the limit as n approaches infinity of a of n, which is our original, over b of n, because that's how the limit comparison test works, which comes out to equal 1. And since a of n over b of n is greater than 0, a of n must also diverge, making b true, our correct answer. Number 6. Use a limit comparison test, if possible, to determine whether the series from n is equal to 1 to infinity of 2 over square root 9 in the front, I don't know how to word that, square root 9 in the front of n squared plus 9. I set my b of n equal to 2 over 9 in the front square root of n squared, because it is the same thing as our a of n without the plus 9. Since b of n is in the p series format and p is less than 1, b of n diverges. By doing limit comparison tests, we find that a of n over b of n is greater than 0. As you can see, we took the limit as n approaches infinity of a of n over b of n, and then just multiplied by the reciprocal, and that got us equal to this, and then which just is, sorry, so that got us equal to this, that becomes 1, and that also becomes 1, plus 9 over n squared, and since we're taking the limit as it reaches infinity, this crosses out, so we get this, which is the same on the top and the bottom, which is equal to 1. And since a of n is a over b of n is greater than 0, a of n diverges, which makes a diverges our correct answer. Number 7. Okay, this is really weird. I have to put number 7 all the way down here. Apologies. Number 7. Find the Maclaurin polynomial for degree 5 for the function f of x is equal to sine of 2 of x. To find the Maclaurin polynomial for degree 5 for the function, I first took the derivative of f of x 5 times for each degree. I then plugged in 0 for the initial x values for every degree I multiplied, and for every degree I multiplied the values for each x1 of x. So basically what I'm saying is that I plugged in 0 to this x, to this x, to this x, and so on, but then I also multiplied this to the power of x times 0, this times x to the power of 0, sorry, which is 1, this times x to the power of 1, which is x, this times x to the power of 2, which is x squared, and then so on and so forth. And so, for example, f prime of 0 was equal to 2, and since it was the first degree, I multiplied it by x to the power of 1, or just x. I also divided it by 1 factorial, or just 1. I did all of this because that is how you find the Maclaurin polynomial for a certain degree. And so I divided it by n factorial, so this was divided by 0 factorial, this divided by 1 factorial, this divided by 2 factorial, so on and so forth. And that is because that is how you're supposed to find the Maclaurin series for a polynomial, regardless of the degree. That's how you do it for every one. Since the second and fourth degrees just equal 0, you don't see them in the final answer because they are 0. Since the third degree comes out to be 4x cubed over 3, or actually it comes out to be 8x cubed over 6, but simplifies to 4x cubed over 3. And the fifth degree comes out to be 32 times x to the 5th over 120, which simplifies to 4x to the 5th over 15. And that means the answer will simplify to A. Going way back up to number 8. Number 8 asks, find the 4th degree Taylor polynomial centered at c is equal to 7 for the function. For the function f of x is equal to ln of x. To find the 4th degree Taylor polynomial centered at c is equal to 7 for the function f of x is equal to ln of x, you must take the derivative of f of x 4 times, once again for each degree. You must then plug in 7 for each x of the derivative. So into this x and this x, this x and this x. And also the very first x as well. And that's because we have our c is equal to 7 up there. Then you must multiply each derivative by x minus 7 to the power of n, with n being equal to the degree you're on, so to the nth degree. So this was multiplied by x minus 7 to the power of 1, this x minus 7 to the power of 2, this x minus 7 to the power of 3, so on and so forth. For example, for the 3rd degree, you must multiply it by x minus 7 to the power of 3, since n is equal to 3. Finally, you must divide by the n factorial. So once again, this is 1 factorial, 2 factorial, 3 factorial. You get the idea. With the 3rd degree, for instance, n factorial is 6, since the n is still equal to 3. So 3 factorial is equal to 6. And then doing that all out and simplifying it and doing all that jazz, we simplify to get C as our answer. Alright, number 9. Identify the interval of convergence of a power series, what we see here. Alright, I think I've given up on reading. I don't know how to say it, but you get the idea. To identify the interval of convergence for the power series of n equals 1 infinity 3, negative 3 to the power of n, and x to the power of n minus 1. You must use the ratio test by taking the limit as n approaches infinity, as we see here, of the absolute value of the series with n plus 1 over the original. Now, I crossed out negative 3 to the power of n on the bottom, and simplified negative 3 to the power of n plus 1 to negative 3. I then crossed out the x to the power of n minus 1 on the bottom, and simplified x to the power of n on the top to just x. I then multiplied the negative 3 you see here, and then the x back here, to become negative 3 of x. I then separated the x plus 1 over n to its own fraction and simplified it to 1, since we were taking the limit as n approaches infinity, and the plus 1 on the top is essentially pointless. So it's n over n, which is 1. We are then left with negative 3x, which becomes 3x due to the absolute value. Also due to the absolute value, we get 3x is less than 1, and 3x is greater than negative 1. Dividing out the 3 on both sides, we get x is less than 1 over 3, and x is greater than 1. X is greater than negative 1 over 3, making C our answer. Moving on to the FRQs. We are started out by given f of x is equal to ln of 1 plus x cubed. The Maclaurin A asks, the Maclaurin series for ln of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and with the general term being negative 1 to the power of n plus 1 times x of n to the power of n. And then the general term that we can see right here. Use the series to write the first 4 non-zero terms and the general term from the Maclaurin series of f. So to find the Maclaurin series of f of x, you must utilize the Maclaurin series for ln of 1 plus x, which we are given right here. Since the only difference between this function and f of x is the x cubed, we must replace every x value within both the general term as well as... we must replace every x value with all the values given here as well as the general term of ln of 1 plus x with x cubed in order to get our answer. Knowing this, we get negative 1, or the series of n equals 1 to infinity, and negative 1 to the power of n plus 1 times x to the power of 3n, since we had to cube it, over n is equal to x cubed minus x to the power of 6 over 2 plus x to the power of 9 over 3 minus x to the power of 12 over 4, etc., etc. And that's how we got our answer.